All right, here are quiz 7 solutions for Math 112. On this quiz, on the first page, what we're doing is we're sketching the graph of tangent and secant of x from the graphs of sine and cosine of x. And then on the second page, we're dealing with some inverse trig functions, specifically function composition with trig and inverse trig functions. So anyways, on the first page, the first problem asks us to come up with the graph of tangent of x. And I think the key thing to recognize if you want to come up with this graph is that tangent of x is the same as sine of x over cosine of x. And that knowledge, along with the graphs of sine of x and cosine of x, will be enough for us to come up with this graph. So the first thing you want to figure out is which of these two provided graphs are sine of x and which are cosine of x. I think the easiest way to get there is by comparing their heights when the angle, the input into the function, the x value here, equals 0. The sine of 0 is 0 and the cosine of 0 is 1. Therefore, the graph in green must be cosine and the graph in blue must be sine. The next step is to recognize that if you try to divide by 0, you get something that's undefined. So because tangent is sine over cosine, anywhere the height of cosine equals 0 will be dividing by 0. So we'll get something that's undefined, which manifests as a vertical asymptote on the graph of tangent of x. What I'm saying is go to your graph of cosine of x, which remember was pictured in green here, and look for anywhere where the height of that graph is 0. So at pi over 2, 3 pi over 2, negative pi over 2, and construct vertical asymptotes at those points. What we can do next is look for points where the graph of tangent of x would have a height of 0. Because a fraction equals 0 when the numerator in that fraction is 0 and the denominator is not, to figure out where the height of this thing is 0, all we have to do is figure out when is the height of sine equal to 0. Because we already decided that the graph in blue was the sine function, what we can do is label any points where the height is 0 and know that those will be on our graph of tangent of x. This might be enough information for you to sketch the graph, but one last thing that I like to do is recognize that a fraction equals 1 anytime the top and the bottom of that fraction are the same value. So anywhere where the height of sine is the same as the height of cosine, in other words, intersections of these two graphs, will give me a height of tangent equal to 1. So right here, where the height in green and the height in blue are the exact same, my graph in red should have a height of 1. Similarly, I have an intersection down here, so the heights are the same, so my graph should have a height of 1. And over here, my graph should have a height of 1. And also over here, my graph should have a height of 1. In the videos I made earlier in this section, I also labeled heights of -1, but I don't even think you need to do that. I think as long as you understand the behavior at asymptotes, we now have enough information to sketch our graph. I can kind of connect these two dots here and make sure that as it approaches this asymptote, it sort of goes up infinitely far. And then on the other side here, it's going to go down infinitely far. And then just copy this basic shape in between all of the other sets of asymptotes. That gives me my graph of y equals tangent of x, which is enough to finish up this problem. Problem 2 is not all that dissimilar, except instead of sketching tangent of x, we're going to sketch secant of x. And just like we did above, expressing that in terms of sine and or cosine will help us come up with the graph. The important thing to know here is that secant is just 1 divided by the cosine of x. So what we'll be doing here is we're only going to look at the graph of cosine. The graph of sine of x will be completely irrelevant to this problem. By the same logic as above, we know that the graph in green is y equals cosine of x. So that's the one we'll be using to sketch y equals secant of x. Same logic, what we want to do first is start with our vertical asymptotes. Vertical asymptotes happen anytime you try to divide by 0. So I'm looking for where the height of the graph in green equals 0. So 3 pi over 2, pi over 2, negative pi over 2, for example, and construct some vertical asymptotes at those points. And then because the reciprocal of 1 is 1 and the reciprocal of -1 is -1, anywhere the height of the graph in green is 1, the height of my graph in red is also going to be 1. And anywhere the height of my graph in green is -1, the height of the graph in red is also going to be -1. And now as long as I understand that in between each set of vertical asymptotes, I either have a U-shaped graph or an upside down U-shaped graph, I have enough information to sketch the graph of secant of x. Between these two vertical asymptotes, for example, I know I have to go through this point, and there's nowhere where I cross the x-axis here, so I must have this right side up U-shaped graph. So more or less something that looks like this. Same logic over here. And then in between these two vertical asymptotes, I have to go through this point, and again, I can't cross the x-axis, so it must be one of these upside down U-shaped graphs. Same logic over here. Not the prettiest thing I've ever drawn, but good enough to get you full credit for the graph of y equals secant of x. We're now done graphing, which I, for one, am pretty excited about, and we're moving on to inverse trig functions. For these inverse trig functions, I really think about them as two different types of problems, even though they look pretty similar. When your inverse trig function is on the outside of the function composition, you use one method, and when it's on the inside, you use a different method. So in my mind, A and B are pretty dissimilar to C, D, and E. For A and B, I'm just going to work from the inside out. I'm going to first evaluate the sine of pi over 2. So on my unit circle, pi over 2 is up here, and this point has a y coordinate of 1, so therefore the sine of pi over 2 is just equal to 1. So I can replace this sine of pi over 2 inside these parentheses with the number 1. What I'm saying is a is the same as the arctangent of 1. For arctangent, you need to know two different things. The first thing you need to know is that my answer is restricted to the right side of my unit circle here. So my answer better be some number in between negative pi over 2 and positive pi over 2. The other thing you need to know is it's asking you the question, what angle in that range will the tangent of that angle be equal to 1? Well, if you think about tangent is the y coordinate divided by the x coordinate, the way a fraction would be equal to 1 is if the top and the bottom of that fraction are the exact same. The place where I get the exact same x and y coordinates over here on the right side of my unit circle is at pi over 4, because at pi over 4, both the x and y coordinates are root 2 over 2. So because the tangent of pi over 4 equals 1 and pi over 4 is in between negative pi over 2 and positive pi over 2, the arctangent of 1 is just equal to pi over 4. So the answer to part A is just pi over 4. Part B, kind of the same logic. I want to start from the inside and work my way out. So let's first evaluate the cosine of pi. Going back to my unit circle, pi is referring to this point over here. This point over here has an x coordinate of negative 1 and a y coordinate of 0. Because I want the cosine of pi, I'm concerned with the x value. So the cosine of pi would be equal to negative 1. So I can replace the cosine of pi inside these parentheses with the number negative 1 and say that part B is really the same as just the arcsine of negative 1. The restriction on arcsine is basically the same as the restriction on arctangent in that I want to look for answers over here on the right side of my unit circle, so a value between negative pi over 2 and positive pi over 2. And now what I'm looking for is an angle in here so that the sine of that angle would be equal to negative 1. Well, let's see, the sine is the y coordinate, and where I have a y coordinate equal to negative 1 is down here. What I'm saying is the sine of negative pi over 2, this point right here, is equal to negative 1. So therefore, the arcsine of negative 1 is equal to negative pi over 2. And you're like, whoa, weird that you're calling it negative pi over 2. I'm used to referring to this point as 3 pi over 2. And that's true, but remember that we restrict the range of arcsine to only include values from negative pi over 2 to positive pi over 2. So my answer has to be a number in that range. 3 pi over 2 is not within that range. Negative pi over 2 is the answer, and I can move on to part C. For what it's worth, I much prefer C, D, E, and even the extra credit problem to A and B. I just think they're a little bit more natural. You have options in terms of how you solve this, but the way I taught you that I think is the easiest is this substitution method. So what you do is you start out by letting t be equal to whatever the inverse trig function is that you have inside these parentheses. So in this case, the arc cosine of root 3 over 2. Okay, well, if t is equal to the arc cosine of root 3 over 2, then this question is really just asking me what is the sine of t. More on that later. What I'm going to do is I'm going to work with this information. If t is the arc cosine of root 3 over 2, then the cosine of t must be equal to the square root of 3 over 2. I can use that information to draw a picture. SOHCAHTOA tells me that if I have a right triangle and I label one of these angles t, then the cosine of t being equal to root 3 over 2 means that the length of the adjacent side to that angle, so adjacent to this angle would be this guy, divided by the length of the hypotenuse is in the ratio root 3 over 2. What I'm saying is because cosine of t equals root 3 over 2, I can label adjacent and hypotenuse to come up with this triangle. If I have two sides of a right triangle, I really have all three because I know the Pythagorean theorem. If I call this, I don't know, b maybe, because a squared plus b squared equals c squared, where a and b are the lengths of the legs of a right triangle and c is the length of the hypotenuse of that right triangle. I can solve for b because I know a is root 3 and c is equal to 2. So I have the square root of 3 squared plus b squared must be equal to 2 squared. So 3 plus b squared has to be equal to 4. So b squared has to be equal to 1. So b is either positive 1 or negative 1, but because I'm talking about side lengths here, it must be positive 1. So now I have this triangle with all three sides labeled, which makes it easy for me to figure out the sine of t. Again, using SOHCAHTOA, the sine of this angle t is the length opposite divided by the hypotenuse. So in this case, 1 divided by 2. The sine of t is 1/2. The answer to part C here is just 1/2. If that made sense, great. If it didn't, well, you got two more chances to go through it. We're going to do the exact same logic for part D here, except now instead of letting t being equal to the arc cosine of root 3 over 2, we'll let t be equal to the arc tangent of 4/3, the inverse trig function that's nested inside this composition. If t is the arctangent of 4/3, then part D is really just asking me for the cosine of t. More on that later. I can use the fact that t equals the arctangent of 4/3 to say that the tangent of t must be equal to 4/3, knowledge that allows me to draw a triangle. If I have a right triangle, my angle T is down here, then I know that since the tangent of T is opposite over adjacent, I can label this opposite side length 4 and this adjacent side length 3. And now I have two sides of a right triangle, so I can solve for the third side. You can either use the Pythagorean theorem or just remember, oh, 3, 4, 5 right triangle is a thing. I'm going to suppose you don't know that and plug in 3 and 4 to A and B respectively and solve for C. I got 3 squared plus 4 squared must be equal to C squared. So 9 plus 16 is C squared. 9 plus 16 is 25. So 25 is C squared. Take the square root of both sides and you get that C is plus or minus 5. But since we're talking about side lengths, it must be positive 5. I have all three sides of this triangle labeled, which makes it easy for me to figure out the cosine of T. Cosine is adjacent over hypotenuse. In this picture, relative to this angle T, 3 is adjacent and 5 is hypotenuse. So the cosine of T is just 3/5. That's the answer to the question. One more time, possibly overkill, but what are you going to do? What I'll do down here is I'm going to let T be equal to the arcsine of 1/4. If the arcsine of 1/4 is just this thing T, then the question is really just asking me what is the cosecant of T. More on that later. If I know that T is the arcsine of 1/4, I can say that the sine of T must be equal to 1/4, information that allows me to draw a right triangle. Because sine is opposite over hypotenuse, I can label this opposite side length 1 and the hypotenuse 4, and then I can solve for this side length using the Pythagorean theorem. I got a squared plus 1 squared is equal to 4 squared. So I got a squared plus 1 is equal to 16. So a squared equals 15. So a is plus or minus the square root of 15. However, since we're talking about side lengths, it must be the positive value. I'm starting to sound like a broken record. What I'm saying is this side length is the square root of 15. I got all three sides of this right triangle labeled, which makes it easy for me to figure out the cosecant of T, relatively easy anyways. If you recognize that cosecant is the reciprocal of sine, then you can figure out the sine of T using this triangle. Sine is opposite over hypotenuse, so the sine of T would be 1/4, but I don't want the sine of T. I want the cosecant of T, so I have to take the reciprocal of that, and it's 4 divided by 1, in other words, just 4. Wait a minute, did I even need to do all that work? The answer is no. I wrote this problem thinking that you could go through it the exact same way we've been solving things, but you could also solve it pretty easily. Right? At this point, when you knew that the sine of T was equal to 1/4, you immediately knew all the information that you needed to figure out cosecant of T. Cosecant of T is the reciprocal of sine. If sine of T is 1/4, you could immediately get that the cosecant of T is just equal to 4. Either way, your answer is 4. You get there, you get full credit. Finally, the extra credit problem. Since it's extra credit, you don't have to do it, but I think this is one of those extra credits that you can get pretty easily. The cosine of the arctangent of x is what we're asked to figure out here. It'll end up being just like what we did in C, D, and E, because we have an inverse trig function nested inside of a trig function. What we want to do is first do a substitution. So in this case, T will be the arctangent of x. If T is the arctangent of x, then the cosine of the arctangent of x is really just the cosine of T. More on that later. If T equals the arctangent of x, then the tangent of T must be equal to x. I'd prefer to write x as a fraction so that I can draw my right triangle. So instead of calling it x, I'm going to call it x over 1. Now I can draw my right triangle here. I always throw T down here. SOHCAHTOA tells me that the tangent of this angle T is the length opposite divided by the length adjacent. So in order for tangent of T to be equal to x over 1, I could draw this triangle with an x over here and a 1 here. And I now know two sides of a right triangle, so I can solve for the third side. Maybe I call it C. A squared plus B squared equals C squared. So 1 squared plus x squared must be equal to C squared. So because 1 squared is just 1, I can take the square root of both sides of the equation and say that C is the square root of 1 plus x squared. And now that I have this right triangle down here, it's easy for me to figure out the cosine of T. The cosine of T is just the length adjacent divided by the length of the hypotenuse. So it's just 1 divided by the square root of 1 plus x squared. This is a perfectly acceptable answer. However, if you feel like rationalizing the denominator, you could multiply the top and the bottom by the square root of 1 plus x squared, and that would give you the square root of 1 plus x squared divided by 1 plus x squared. Either of these are totally acceptable and would get you the extra credit.